Welcome back to Math 1324. We are in Chapter 4, Systems of Linear Equations and Matrices. And today we're going to talk about Gauss-Jordan elimination, Section 3. So, reduced matrices. In the preceding section, so Section 2, we saw systems of linear equations using augmented matrix methods. This process is referred to as Gauss-Jordan elimination. So there's your first vocab word. It's referred to as Gauss-Jordan elimination. I recall from the last section, we wanted to use Gauss-Jordan elimination to get the augmented matrix into one of the we wanted to use Gauss-Jordan elimination to get the augmented matrix into one of these simplified forms. Remember where we had the 1, 0, 0, 1 on the left-hand side of the big bar? That gave you one unique solution. Or you had a row of all zeros, in which case there were infinitely many solutions. Or you had a row of zeros to the left of that bar and a number that was not zero to the right of the bar, in which case you had no solution. All right, now we will consider systems involving more than two variables. Any linear system, regardless of the number of equations or number of variables, has either exactly one solution, infinitely many solutions, or no solution. So what does it mean for a matrix to be in reduced row echelon form? Or sometimes you'll see it just called reduced form. Okay, there's four conditions that have to be satisfied. First, each row consisting entirely of zeros is below any row having at least one non-zero element. So if you have a row that has all zeros, it has to be at the bottom. Second condition, the leftmost non-zero element in each row is a 1. The leftmost non-zero element in each row is a 1. In other words, reading from left to right, the row has to start with a 1. Okay, number 3, all other elements in the column containing the leftmost one of a given row are zeros. And the fourth condition, the leftmost one in any row is to the right of the leftmost one in the row that's above it. Okay, let's go look and see how this holds. Okay, examples. The following matrices are not in reduced form. Which condition of the definition is violated? So first thing, are there any rows of all zeros in this example? And the answer is no, so that condition is okay. Number 2, the leftmost non-zero element in each row is a 1. So for row 1, the first non-zero element is a 1. That's okay. But look here at row 2. The leftmost non-zero is a 3. So I'm going to say that condition 2 is not met. And I'm going to go circle that 3. All right, let's go look at number 2. Okay, there are no non-zero rows, so condition 1 is okay. The leftmost non-zero element in each row is a 1. So let's look here at row 1. Yep. Row 2. Yes. Okay, all other elements in the column containing that leftmost one of a given row are zeros. So looking here, other than that leading 1, every other element is a 0. Same there. So condition 3 is met. Condition 4, the leftmost one in any row is to the right of the leftmost one in the row above it. In other words, the ones have to go down a diagonal like that. you can see that that condition is violated. So on example number 2, condition 4 is not met, meaning those ones aren't going down the diagonal this way. Okay, let's look at number 3. Oh, right off the bat, I see a row of zeros right there. Condition 1 says each row consisting entirely of zeros is below any row having at least one non-zero element. So condition 1 is not met. Because that row of zeros should be at the very bottom. It should be row number 3. All right. Solving systems by Gauss-Jordan elimination. The procedure. You're going to choose the leftmost non-zero column and use appropriate row operation to get a 1 at the top. You want a 1 at the top. Then you're going to use multiples of the row containing the 1 from step 1 to get zeros in all remaining places in the column containing that 1. Then you're going to repeat step 1 with a submatrix formed, deleting the row used in step 2 and all rows above that row. And you're going to repeat step 2 with the entire matrix, including the rows deleted mentally. You continue that process until the entire matrix is in reduced form. All right. Before we go do that, that's a lot of words, and you probably just listened to me read it and then did not comprehend a thing. That's okay. Before we go do this, let's look at some matrices and write the solution. So right now, I want you to look at this augmented matrix and give me the solution. Do you see that you have a row, a diagonal of all ones? That's good. That first row says that x equals 2. That second row says that y equals 0. And that third row says that z equals 0. So I would like to write it as the ordered triple 2, 0, 0. Now, number 2. If I look at the diagonal, I get into trouble there right here. That draws my attention to row number 3. I see that 0 is supposed to equal 8. That can't happen. My answer is no solution. Again, look for that diagonal of ones. Uh-oh, I see trouble there. So then I go back and say, okay, look at that row number 3. It's all zeros. That's good. That means there are infinitely many, infinitely many solutions. But now we want to get a way to write what those solutions are. So this is a new concept for some of you. Looking at row number 1. Okay, remember that I'm dealing with variables x, y, and z. Row number 1 tells me that x plus 7z equals 1. X plus 7z equals 1. Let's solve for x. I'm going to move 7z to the other side. That tells me that x is equal to 1 minus 7z. Okay, now let's look at row number 2. What does row number 2 tell us? Row number 2 says that y plus 3z equals negative 1. So y plus 3z equals negative 1. Solving for y in terms of z, subtract 3z from both sides, and I get y equals negative 1 minus 3z. Now, remember that row number 3 was all zeros, right? So that means that Z can be anything. So when I write my ordered triple, I'm going to write X is 1 minus 7Z, Y is negative 1 minus 3Z, and Z can be anything. Now, most books, instead of telling you to write Z, they're going to tell you to replace that with another variable. And most of the time they use the letter T. So the Z variable can be anything, but the X and the Y depend on what that Z variable is. So if you let Z be T, then X is going to be 1 minus 7T, and Y is going to be negative 1 minus 3T. Okay, number 4. I see a row of all zeros. So I'm going to have to introduce a parameter, which was that T in example number 3. It's called a parameter. But let's go look at row number 1. Okay, row number 1 tells me that I have X minus 5Y equals 9. So if I add 5Y to both sides, I get that X equals 9 plus 5Y. Okay, row number 2. Row number 2 tells me that Z equals 0. Okay, what letter am I missing? What letter does this row of all zeros represent? It's the Y variable, because I have the X in terms of Y. I know that Z is always 0. So here we go. My X is 9 plus 5Y. Y can be anything, and Z has to be 0. Now, again, most books will tell you to put T instead of the variable that can be anything. So my solution would be 9 plus 5T, T, 0. Okay, for number 5, I'm looking for a diagonal. Oh, wait a minute. I see a leading 1 here in row 1, a leading 1 in row 2. Oh, that's okay. I see a leading 1 in row 3 as well. Okay, with this matrix, this note here, if the number of leftmost ones in a reduced augmented coefficient matrix is less than the number of variables in the system, then there are not going to be any contradictions. So the system is going to be dependent, and it's going to have infinitely many solutions. What that means, okay, variables, X's, Y's, Z's. Uh-oh, we need a couple more variables. Let's call this T and W. All right, row 1 tells me that X minus 3Z plus 4W is equal to 3. I want to get the X by itself. I'm going to add 3Z and subtract 4W from both sides. My X in terms of the other variables equals 3 plus 3Z minus 4Z, minus 4W. Okay, row number 2. Row number 2 tells me that Y plus 2Z plus 2W equals negative 6. So subtracting 2Z and subtracting 2W from both sides will leave me with Y equals negative 6 minus 2Z minus 2W. So I solved for x, I solved for y. This third row tells me that p minus w equals 0. So solving for p, I get p equals w. All right, for my answer, I want an x, y, z, t, w. I solved for x. It was equal to 3 plus 3z minus 4w. Did I solve for y? Yes. Y was equal to negative 6 minus 2z minus 2w. Did I solve for z? No. So it's just z. Did I solve for t? Yes, it was w. Did I solve for w? Nope, it was just w. I would leave your answer like this. Back here, where it was just one variable that was missing, you could let z be t, or this one actually was y. Let y be t. I would just have left it y, especially with an example like number 5.